particular learning method sort of way. Okay, so hopefully, I think probably fairly quick. I just want to sort of fairly quickly go through, just to give you a different picture, right? Sort of vertical picture, since most of our time we will spend sort of in this way, right? Not this way. Okay. Okay, so logistic regression. So first of all, what is it that we are interested in? In logistic regression, we are interested in the probability, right? We're actually interested in regression. We actually want the probability, or at least maybe we finally actually use it just to do classification, but it's going to output a probability of y given x, right? Y equals to 1 given x, and we represent it this way. Right, this is the logistic function, and it has a nice property that it goes from 0 to 1. Right, goes from 0 to 1 in a S sort of way. Okay, then the loss function that we use often, right, is the log likelihood, if you like, is the log loss. Right, often log likelihood also correspond to minimizing the description length. Right, if I want to encode the log loss will actually minimize the description length, the information, right? So in logistic regression, we do the log loss, which looks like this, right? Where, okay, to write it this way, we need y to be minus 1, 1, right? So the nice thing about this loss function is convex, and it's lip switch. Okay, lip switch, we don't get confused, we actually look at it two ways, right? One is with respect to this whole thing, right? And in that case, the lip switch constant is 1. Okay, with respect to this as the argument. But if it's with respect to x, with respect to w, then the lip switch constant is actually max of the 2 norm of x. Okay, so don't get confused. We use it in two ways. Okay, so the loss function is convex, so it's lip switch. With rho less than lip switch constant less than equal to the max of the input, L2 norm of input. So what do we normally do? We want to minimize the empirical risk, right? If you write it this way, this is also convex and also lip switch with the same constant. So that means we can, so you can optimize this in many ways. One of the algorithms we look at is gradient descent. So if we do gradient descent and we assume that the weight vector is bounded, then gradient descent is going to minimize all we can project back to this ball, if you want to keep it in this ball, or you want to compete with weight vectors within this ball, then this number of iterations is sufficient for gradient descent. Right, so this is b squared, rho squared. Rho is this guy, right? So it's something like 1 over epsilon squared. And stochastic gradient descent also works, but it gives us the expected error, right? That's not the deterministic error, but the expected error. In practice, you can make it faster for this problem using sort of second order method. Faster or not depends, right, on different things, the accuracy you want, and so on. In practice, we usually use regularization, L2 and L1 regularization common. Okay, and both seem to work reasonably in practice. L1 gives sparse solutions, so that's if you're interested in sparse solution, L1 gives sparse solution. Yeah, so you can, again, if you want to optimize this, you can use gradient descent, or in this case, it's subgradient, right? It's not differentiable anyway, so it's more subgradient descent. Okay, so that's sort of from the optimization side. Okay, then we also look at generalization. How much? What's the generalization error? Or how many examples do you need to get to a certain error? So again, for the analysis, we assume that the weights is bounded in a ball, the input is bounded in a ball, and the input size is bounded. And we have lip switch for logistic regression. The lip switch constant is 1. There's a row here in the bound, right? So yeah, so you get this sort of bound. So what are the things that are interesting? probably the bound goes down as square root of m, where m is the training set size. Right, again, different. If you do some slightly different analysis, you might get slightly different bounds. But it's 1 on square root n. Sometimes maybe 1 on logistic regression. Probably not. But in some cases, you can get 1 on m sort of bounds. Okay. And right, it's sort of roughly proportional to dr. So if you want to ask, can I do this efficiently? Then you look at how many rounds do I need? Right, that's polynomial with respect to epsilon square. And then you ask how big the m do I need? Right, that's again going to be polynomial with respect to 1 over epsilon. The runtime is more or less proportional to m. So everything's going to be polynomial with all these things. Okay, so that, if you like, it's an example of being able to do the whole thing in polynomial time. Okay. To get to a certain expected error with high probability. Okay, so if you want to do the L1 norm, you get a slightly different bound. So interesting things to look at maybe is, so this one actually, right, this one depends on the input dimension and is log of the input dimension. Okay, so it's quite, as the number of features grow, it doesn't go too badly. Doesn't do too badly. Otherwise, right, it's sort of similar, BR over M. Okay, so the other thing that might be interesting is that this actually doesn't depend on D. It doesn't depend on the input dimension. So we can actually kernelize it and it still holds, the bound still holds. So, yeah, so we can, people do logistic regression and often they're interested in classification and you can just threshold, do thresholding. So the logistic loss is actually convex, and so in the upper bounds, if you scale it a little bit, this one doesn't quite, you need to scale it with a constant, and you're actually upper bound your 0,1 loss. So it's actually, we've mentioned a few times, a convex surrogate loss, right? If you're actually interested in classification, but the data's noisy, to minimize the classification error on the training set, that's actually computationally difficult. So one trick you do is you use a different loss function, and then this loss function will upper bound the classification error, right, the 0,1 loss. So logistic loss has those properties. We can extend it. In practice, often you might be interested in actually multi-class problem. So softmax, instead of logistic regression, this is softmax regression. I guess for this course, we didn't analyze this in any detail, but it is extendable to softmax regression. If you look at different areas, they call it different names. Often it's called maximum entropy, log linear classifier, logic regression, softmax regression. They're all essentially the same thing. And right, like I said just now, in terms of the error bound, actually, it doesn't depend on D. So in terms of the algorithm, right, you can kernelize it and it's still efficient. In terms of the sample size, it's still right. The bound still holds. Okay. If you use kernels to sort of extend to nonlinear classifier. So that's logistic regression. Okay, support vector machine. Very similar actually to logistic regression, except we use the hinge loss. Right, so hinge loss is max of 0 and 1 minus y of ux. So again, the hinge loss actually upper bounds the 0,1 loss, so it's a convex surrogate loss. It's convex. And people actually do use it. They say, I don't know how to minimize this linear function for a classifier because it's computationally hard. So let me just replace it with this. This is actually the motivation people use this. Replace it with this, and then it becomes a convex optimization problem. So all the bounds actually is the same as the logistic regression because it's the Lipschitz constant is the same. Okay, so all the bounds for gradient descent and the sample complexity is actually the same. Okay, so that's one benefit of making it general, abstract. They are all the same. Okay. But there are some differences, right? So, for SVM, we usually minimize this because we want to regularize. Often we use stochastic gradient descent in practice. So one well-known algorithm is Pegasus. No, essentially it's just running stochastic gradient descent by the textbook author, Charles Schwartz. Okay, so that's one algorithm. If you do optimization, you might learn a lot of other optimization algorithms. So in practice, people use it. But often they optimize the dual instead of the primary. Okay, so generalization bound essentially is the same as logistic regression. Okay, the hinge loss is at least interesting or useful to analyze things in terms of the margin. Right? Now quite often it's at least conceptually interesting to think of the margin. Right? So if we set the margin to be at least 1, right, then the hinge loss will have value 0 for all examples. Right? If you look at the hinge loss, it's the max of, so if this is always at least 1, then the max is always going to be 0. Right? 1 minus something bigger than 1 negative, so the max is always 0. So that means this term is actually going to be 0. Right? So that allows us to say that the expected loss is less than this. And if we want to look at the impact of margins, right, to say if you have large margin, then you actually do well. Okay, when we want to talk about margin, normally we would rescale and say that B is the size of the weight. Right? That the size of the weight is 1. If we rescale and say the size of the weight is 1, then the margin is 1 over B. Okay, you plug it in to get this, which tells us that if you have a large margin, then you have at least small upper bound on the generalization error. Okay, so that's at least in support vector machine, people like to think about margins, right? Distance from the decision boundary of the data point. Okay. Can be kernelized, and people often, the logistic regression not so often. Probably one reason is actually it gives a sparse solution. The support vector machine gives a sparse solution, and that's useful because it speeds up your algorithm, both when you do training, optimization, as well as when you do classification. Sparse in what sense? In the sense that the weight vector is actually a linear combination of a small number of training examples, the features of a small number of training examples. Okay, and when your feature is sort of infinite dimension and can be described as a kernel, that means the weight is sort of the sum of a small number of kernels, right, centered or at a small number of training examples. Okay, and that's useful because that allows you to speed things up. So support vector machine, when you do kernelization, usually often people use support vector machine. Okay, and quite effective in practice. I think so roughly that's my summary of support vector machine. Decision trees don't have that much to say. You can bound the generalization error again, so it's an interesting example of using minimum description length. Generalization error depends on the size, essentially the number of nodes, size of the tree. Okay, the bigger the tree, the poorer the bound. Okay, the training is sort of a greedy algorithm. Just now we did convex problem. This one,